I will. Oh, it's working. I will. I will begin with a word of prayer. Dear Father, we thank you for this day. I thank you for these students, and just help us to use this time wisely. Lord, in your name I pray. Amen. So, do you guys have questions about? Start with one. It's okay, my computer's still deep in thought at the moment. Oh, there it is. Let's see here. Isomorphism? Sure. Uh-huh. So let's see here. So we say V and W are isomorphic F vector spaces if they're both V and W are vector spaces over F, right? And there exists an invertible linear map. I often use psi, which goes from V to W. Some practical comments. So if the dimension of V is equal to the dimension of W, then V is isomorphic to W. Right. That's true. So to judge whether or not it's possible to find an isomorphism between two spaces, it suffices to figure out if they have the same dimension as a real or complex or whatever vector space. If beta is equal to V1, V2, Vn, and gamma is W1, W2, Wn, are bases for V and W respective, then if you say T of Vi equals to Wi for I equals to 1, 2, n, right? So define a map by mapping the ith basis of V to the ith basis of W, all right? If you do this, then you can uniquely extend that map to get an isomorphism. So often this is how I construct isomorphisms. I find a basis for one space, I find a basis for the other space, I map my given basis to the other basis, and then extend linearly. That defines an isomorphism. So that's often, if the example is not super, super easy, like this is a helpful guide. A lot of times, though, I just kind of look at it and write it down. I mean, a more honest advice for most examples, though, is the following, which is to identify free parameters describing typical element in V and W and map them. So the thing I wrote in red is often how I actually operate for specific examples. Let's look at a specific example. That's what you guys want, right? So here, we could look at, say, V equals to A in our 3 by 3 such that the trace of A is equal to 0, and E1 transpose A E3 equals to E2 transpose A E1, and A E1 equals to A E3. There's kind of a weird subspace. We never had quite that example before, but I'm pretty sure that defines a subspace, all right? And then let's see here. What do you guys want to find an isomorphism to? Let's find isomorphisms of this to a couple different things if possible, right? So here's what we'll do. We'll see if we can find an isomorphism to, let's see here, part A, we'll do Cn as real vector space, okay? And then B, PNR, all right? So before we even get into any details, can we think ahead? So if the dimension, right, if the dimension of V is odd, then we're going to be in trouble. See, because the dimension of Cn as a real vector space is 2n. So this is only going to be possible for part A if the dimension happens to be even. I have no idea if the dimension of V is even or odd at the moment. I just made this up, you know. So what I do when I have this sort of new example that I don't have, this isn't like that problem on the test where we had the W1 and W2 where we have existing tools like factor theorem. You know, this one we just have to kind of, if you have a subset of symmetric or anti-symmetric matrices, you see that on the test, it shouldn't be the first time you've seen it, right? But this is new, right? So what I do is I just write down sort of a generic, what I have to work with here, A11, A12, A13, A21, A22, A23, A31, A32, A33, right? That's like a typical, just arbitrary element that V is, that's the blank template on which, blank canvas rather, on which V is being sort of painted. And then let's just dissect these different conditions, right? I think the easiest condition to understand is this last one. What does that condition on V say? It says column 1 of A is equal to column 3 of A, right? The middle condition here, what's star say? Remember what it means? E1 transpose AE3. That gives us the first component of column 3. So that's actually A13 equals to A21, yeah? So All right. I think at this point I'm going to invent some new letters just to simplify my life because, you know, the double subscripts is kind of being a drag at the moment. So I think it's helpful to use ABC maybe. Let's let this be ABC. All right. So I've got A is equal to A, B, C. A, B, C. What else do I know, though? 1, 3 is 2, 1, right? 1, 3 is equal to A2, 1. That's, what's that?
Oh.
Did I do it wrong?
No, I'm just saying, like, so A and B are equal.
A and B are equal, right. So I don't need ABC. I can go A, right? All right. I think that's going to be it for the second and the third condition defining my V, right? So do you guys want to stick with A1, 1, 2, A2, 2, A3, 2? I don't. I want to go and say D, E, F, right? Just because, well, less writing. And trace of A then is equal to A plus E plus C. And we said that the trace was 0, right? So that means we can get rid of one of the letters in place of the other two. Let's get rid of E so that we, well, I don't know. What do you, I guess I'll get rid of C. C is kind of, I'll just get, choices, right? So yeah, C is equal to minus A minus E, let's say. And so generically speaking, I have A is equal to A, D, A, E, A, minus A, minus E, F, minus A, minus E. So I'm actually using the third bullet point as my method to find the isomorphism here because that just seems like the most convenient method for this problem. So I've used all of the given conditions, right? I've exploited them to the fullest. I've identified what are the free parameters that describe a typical element in V. So what's the dimension of V? A, D, E, F. It's 4-dimensional.
So you just counted all of the letters.
Right. This only works if you're careful to have imposed all of the conditions and your letters are genuinely independent. They have to be free parameters, unbound one to another. The counting here makes a lot of sense. This is a column equation. That's 3 equations. This is a single equation. That just equates the 1, 3, and 2, 1 components. And this is also a single equation. It says that the sum of the diagonal elements is 0. So you've got 1, 2, 2 plus 3, 5. And these equations are independent. It's fairly obvious that these are not the same equation, and they're not like linear combinations of the equation. So it's not surprising to me that we had, what's the dimension of the backdrop here? We're drawing on a 9-dimensional canvas because the dimension of our 3x3 is 9-dimensional. So 9 minus 5 is 4. It makes sense that we got a 4-dimensional. Just some counting like that you can do. If you didn't know for sure that these conditions were independent, that would mean that you could have if there was actually some like interdependence among the equations, then you wouldn't drop dimension from 9 as much. Like you might only have a 5-dimensional space instead of 4. All right. But anyway, what's the isomorphism? So is it possible to find isomorphism to Cn? Absolutely. Right. So for part A, I would just, and keeping with this formula right here, okay, I would just say psi of A equals 2, and then I just build a typical element in C2 using parameters, right? So like, here, I'll do it. A plus ID, comma, E plus IF. That would be an isomorphism to C2, which is 4-dimensional.
But there are other options.
Oh, absolutely. You could just as well have done E plus IA, F plus ID. I mean, there's infinitely many options. There are many, 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 many choices. How about to answer part B, what would be? So I like this kind of question because it, you know, so it's not, you know, if I tell you find an isomorphism to C2, there's like less for me to, I can see less about my students than I'll leave it open, say if possible, you know. So we figured out that n had to be equal to 2 here. Pn is the span of what? 1x, x squared, x to the n, right? What's the dimension of Pn? What's the dimension of P2? So,
So if it's 1x, x squared, you have the 1, and then you have, so it's like, is it the n plus 1?
n plus 1, that's right, yeah. Because this is we proved this was linearly independent, remember, by like plugging in 0 and then differentiating, blah, 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 blah. So this is linearly independent. It's essentially, by definition, the spanning set, a generating set for Pn. N plus 1 things, that means it's dimension n plus 1, right? So if we want dimension n plus 1, what should we be looking for isomorphism for part B? An isomorphism into what? Not P4, but P... other way around. P3, right? So if you think about this less abstractly and just think about writing down the formula, you figure it out. It's just the way I'm asking the question is confusing you. Sorry. But how about this? A plus dx plus ex squared plus fx cubed. There you go. That's an element of P3R. There's, in fact, of course, an isomorphism to cubic polynomials. Now, figuring out, you know, like the target for these isomorphisms is kind of easy because the vector spaces I gave you as targets, Cn and Pn, they're sort of unadorned, right? I mean, they're just kind of the whole thing. This question gets a little bit trickier if I give you something to find the isomorphism to that's a little bit less easy, you know, like W, a subspace, W equal to, you know, f of x in Pn such that f of 1 equals to 0. Like, so look at the subspace of nth order polynomials which take 1 as a 0. What does that look like?
I remember doing something where, like, so it'd be like x minus 1 because it's f1.
Ah, right. So do it over here, but yeah, w would be equal to, you said it would be equal to something like x minus 1 times g of x, such that g of x is where? Yeah, Pn. But if this is a subset of Pn, then g of x has to be in Pn minus 1, right? Because otherwise the product wouldn't be. I mean, if I want this to be a subset of nth order, that means that the factor has to be n minus 1th order, right? And so if we just, write this out, that's something like x minus 1 times like a0 plus a1x plus an x to the n, right? So what I'm trying to get us to is to notice that something like this is really the span of x minus 1 and x times x minus 1, xn times x minus 1. And you could prove that those are linearly independent. And how many of them are there? It's like this. This was n plus 1 dimensional. We took that, we subjected it to the condition that we have a 0 at 1. You told me factor theorem does that. Good. And I just found the basis for it with this 1, 2, n things. So we take an n plus 1 dimensional thing, we put one condition on it, it gives us an n dimensional thing. So this is n dimensional. So going back to my question, can we find an isomorphism to W? What would psi of A be in this case? More specific, I mean, we're going to put n equals to 4, right? So that's,
I was just going to say somehow we need to.
so here's if I use my second bullet point as a guide, essentially I try to map basis to basis, right? So like I do something like, I don't know, maybe this is the better way to do it though. Like think about this way of this formulation of W is easier. So I would just let psi of A be x minus 1 times, A plus dx plus ex squared plus fx cubed. Wait a minute. Oh, yeah. There you go. That would give an isomorphism to W. Does that make sense? I'll be right back. Is there a lab in there?
Yes.
When?
It's supposed to start in about 10 minutes.
Aw, phooey. minutes. Does it actually start at 9?
I think might be 9:10, 9:15. I don't know. Sometime between 9 and 9:30 is when we start.
The class starts at 9:20.
Well, it's Thursday, so
It's Thursday.
9:45.
Like I said, we start sometime between 9 and 9:30.
All right. Okay, thank you. All right, well, I'm not sure how much longer we have. Sorry, I've spent a long time talking about this problem. I hope it's helpful. I don't know. You know, there are other things that are just easier, right? Like if I say, find an isomorphism from, say, C2 by 3 to Rn for appropriate n, that's easier, right? So like there is your typical 2 by 3 complex matrix. And I'm finding isomorphism as real vector spaces. So what's your n? What's the dimension of this? It's 6 complex dimension, but it's 12 real dimensions, right? Because you got, so if you look at here, Z1, Z2, W1, and so this would be, make it 12, right? And so, I mean, I would just do this, Z1, Z2, W1, W2, U1, U2, V1, V2, X1, X2, Y1, Y2. What I'm trying to say is not every example requires this kind of like delicate thinking. Some of them you should just be able to kind of like look at and go, oh, that. And what is this, by the way? This is the coordinate map for what basis? Calling this thing, we call this thing M because I don't want to write it again. Can you see? I mean, that really is just the. I need to make sure I can actually see all that I wrote out in the camera. Otherwise, I feel like, okay, good. I was worried about like line of sight, you know, like, but what's the basis that that's the coordinate map for? Because coordinate map is an isomorphism, guys. The coordinate map is an isomorphism of the vector space in Fn, or Rn, you know, or Cn. So M is Z1 times 1, 0, 0, 0, 0, 0, right? Plus Z2 times I, 0, 0, 0, 0, right? Plus dot, 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 plus Y1 times 0, 0, 0, 0, 0, 1, plus Y2 times I times 0, 0, 0, 0, 0, 1. What are those? Well, there's a lazier notation, right? This is E11, this is IE11, this is E3, 23, and this is IE23. So the answer to my question is that beta is E, I, J. Oh, I is a poor choice here. E. Yeah, okay, EKJ, comma, I. Ah, stink. The ordering matters. I was hoping to be lazier, but I got to list them. Dang it. Fine. E1, 1, IE1, 1, E1, 2, IE1, 2, E1, 3, IE1, 3, E2, 1, IE2, 1, E2, 2, IE2, 2, E2, 3, this is what I get for giving you a 12-dimensional example. It's my own stupid fault. I could just as well have made this example with a 2 by 2 complex matrix, right? And I've lost nothing. These are the kind of poor choices I make every day. What can I tell you? Ooh, a turbocharger. Or not. What is this? Apple. Ugh. Yeah. But, you know, this is another generic bullet point I might make. If I ask you to find an isomorphism from your given vector space, if it's a vector space over R, if I say find an isomorphism to Rn, really I'm saying find a coordinate map. If you have a complex vector space and I say find an isomorphism to Cn, that's just a kind of sideways way of asking you to find a complex coordinate map. So coordinates, the coordinate maps are probably the most important isomorphism in this course and the one that we keep using throughout. Even when the problem's not about coordinates, sometimes it's about coordinates, right? Like problem 4 on the test, find the ABC, condition on ABC for which it's a basis. You know, the way I solved that was to change it to a problem in R3 using coordinates. If you watched yesterday, you can see I did there. Probably have time for like one more question before we get run out of here. You have any questions? Do you have any questions about mission 7? I can.
Probably. Yeah.
Haven't had a chance to look at it yet.
I started reading the notes, but I haven't started the mission yet.
I would recommend a sort of staggered approach. Like it's wise to take a like.
Oh yeah, because that is heavy reading.
Right.
I try to take notes.
Right. If you get stuck on something in the notes, just send. You know, if a particular paragraph doesn't make any sense, just email me. I'm happy to.
I'll email you a couple times a day.
That's fine. So mission 7, right?
Yeah. Also, it says chapter 7 of the notes. Is it supposed to be chapter 8?
Yeah. Well, yes.
I don't think most people read the notes anyways.
Yes.
Honest.
Yes and no. I mean, the direct sum stuff is that the end of chapter 7.
Yeah.
So let me just make some comments. Problem 109. You're supposed to show that W1 direct sum W2 is R4. So what would be, there's various ways you could do this, right? Remember in the notes, we have a theorem of equivalence at the end of chapter 7. You may recall me saying something about I had 4 equivalent conditions and then Kang is like, but also 0. I'm like, yes, thank you. So it was 4, and then Kang made it 5. There's a list of, oh yeah, there it is. It's on page 208 or so. Theorem 7.9.4. Theorem 7.9.4. That allows you to make, well, quick work of problem, if I can find it again. Where'd it go? 109. So what is one of the things that theorem says? It says that if you can take a basis, so like I think, personally, I think the easiest way to do it would be part 4, use part 4. It says if you've got basis beta 1 for W1 and basis beta 2 for W2, right? And beta equal to beta 1 union beta 2 is basis for V, right? Which in this case would be R4. If you could show that the union of the bases for W1 and W2 formed a basis for the whole space, then that would suffice to prove it's a direct sum decomposition. So what do you think the basis is for? Are you looking at the problem?
Yeah.
What do you think the basis is for? So you guys tell me, what's the basis for W1? Right? Are those linearly independent? Clearly so, right? One's not multiple of the other. You can see it. You don't need to calculate anything. It's just manifest. And then how about W2? What's the basis for W2? Right, exactly what's listed there. So how do you decide whether when you put all of those 4 vectors together, they form a basis for R4? How do you test linear independence of 4 vectors, 4 4-dimensional vectors? What's the easiest way? The hard way is to put them in a 4x4 matrix and do row reduction until you get the identity.
I was going to say that, so.
What's a lazier way? If you're just asking the question, are they... Ah. How about this? A invertible if and only if columns of A are linearly independent, if and only if AX equals to 0 has only x equal to 0 solution, right? If and only if what? This is for A and Rn by Fn by n. These are equivalent conditions for an invertible matrix. What was one of the conditions which is most easy to check? Determinant, right? Not equal to 0. So all you got to do is take the vectors which generate W1, the vectors which generate W2, put them on a big, concatenate them, glue them together into a basis for R4, take the determinant of the corresponding basis matrix. If that's non-zero, you've proved it's a basis, and then by theorem 7.9.4, part 4, you've proved that W1 direct sum W2 is R4. That's the smart way to do that problem. There are other ways. So there's a bit of advice for you. But I'll stop there for today. All right? Yep. We may actually have longer. They don't know when class starts, so just in the